So this is problem solving lecture 20. The second part of the exam, questions 6, 7, and 8 are face down. Don't start looking at the problems until you are ready not to be talking to me anymore. Because once you start looking at them, I can't, of course, talk to you about the material. I've also emailed them to you as well. Okay, there's also no real homework for this coming week because you can be working on those as the homework problem. Pick up old stuff later on. What we're going to do today is we're going to continue with standard integration techniques, and then on Monday we will switch and we will start the complex analysis blitzkrieg. So we will do the complex analysis that's useful in either 1 or 2 lectures, I think. And it'll be a good way to talk about some results from real analysis, some sequences and series, and motivate why we spend all of our time worrying about these convergence stuff. What can you do with this? And it turns out you convert all of these integration problems to Taylor expansions. Well, actually a little bit more general than a Taylor series expansion. A Taylor series expansion is a sum n goes from 0 to infinity. You could also sometimes have negative terms, 1 over x squared, 1 over x cubed. And it turns out the 1 over x is the most important. And we'll see why that's the most important. There's actually a reason that it goes back to something you've seen in Calc 1, but not surprisingly was not emphasized at the time. And you'll see why all of complex analysis really comes down to this one wonderful fact. And then you'll see how to convert finding integrals to Taylor expanding certain functions and finding their negative first coefficient. And it's now just algebra. So it's a wonderful technique. Now, after giving you all this great motivation for why we're going to do this wonderful stuff next week, I've got to have something good to talk about now as well. Otherwise, it's like, why are we doing this? Why don't we just get to the good stuff? All right. So what I want to do today is I want to talk about differentiating identities. So how many of you have seen differentiating identities before? Okay. So differentiating identities is one of the best techniques we have for solving problems. And one of the places it's most used is in probability. So to give you a sense as to why we care so much about differentiating identities, we spend a lot of time proving inequality in mathematics. And the equalities are our bread and butter. If I could give you a procedure that would take as input an identity and spit out infinitely many more identities, this would be useful. That's what differentiating identities do. And I think it's quite clear what the technique is you use to get the additional identities. And so the idea is, if you spend a lot of time proving one result, you can often get a whole slew of results for free. Now, frequently you will need to justify interchanging a derivative and an integral, or a derivative and a sum. If things are finite, there's no problem. So if your things are nice continuous, if the integral of the absolute value is finite, if the region is finite, usually you can justify it without any trouble. The difficulty is when maybe the integral of the absolute value blows up, or you have a sum over an infinite space. Then you have to worry about how things are done. So quick probability review. So we say P is a density if P of x is greater than or equal to 0, and the integral from minus infinity to infinity of P of x dx equals 1. Frequently what we'll do is we'll say x is a random variable with density f sub x. And we frequently put the sub x over there to remind ourselves which random variable is in play. If there's only one random variable in the problem, it's not so important. But the more involved things you study, the more important it's going to be. If I had a discrete random variable rather than a continuous one, I would replace the integral with the sum. You could, of course, have something that is a mix. It's discrete in some places and continuous in others. For the most part, we'll deal with pure continuous or pure discrete. So one of the great difficulties is making sure that things integrate to 1. If the integral is finite and non-zero and your integrand is non-negative, you can always rescale it. So for example, if I give you the integral from minus infinity to infinity of 1 over 1 plus x squared dx, this is just twice the integral from 0 to infinity of 1 over 1 plus x squared dx. This is twice arctangent of infinity minus arctangent of 0. We've done the arctangent before for this, I think? Yes. Okay. Arctangent of 0 is 0. Arctangent of infinity is pi over 2. So this is just going to be pi. So this is not a probability distribution. It doesn't integrate to 1. But it's non-negative and it has a finite integral. So what we can do is we'll study what's called the Cauchy distribution. So how do you think I should modify this distribution? Yeah, put a 1 over pi. So it's not that hard to renormalize this and make it a probability distribution. Okay? In general, it's very tough sometimes to figure out exactly what the normalization constant is. Proving that there's a normalization constant isn't so bad. But actually determining what the normalization constant is, that requires a little bit of work. Okay, and so the camera does not seem to like where I have positioned it today. Working. All right. So we'll see how it works. All right. Okay, so for example, if we integrate from minus infinity to infinity of e to the negative x squared over 2 dx, this is related to the Gaussian. Have we done this integral yet? We did this as did we do this as squaring the integral? You haven't done this one yet? Okay. Since we're talking about integration techniques, this is a good one to do. So has anyone seen this integral before? Okay.
All right. The negative x squared? I've seen positive x squared.
Positive x squared would blow up.
Oh, right.
So
Yeah,
it's got to be negative x squared.
Yeah, I think I saw it's integrated with polar coordinates.
It's integrated with polar coordinates. So if you call this integral I, then I squared is equal to minus infinity to infinity e to the minus x squared over 2 dx integral minus infinity to infinity e to the minus y squared over 2 dy. I can't use the same letter twice. Well, I could because they're dummy integrals, but if I use the same letter, I lose a little bit of freedom. If I use different letters, I can actually combine this as a double integral. And notice that we're going to have an e to the negative x squared plus y squared. When you see x squared plus y squared, you should be thinking polar. This is one of our big techniques. So I squared is the integral minus infinity to infinity e to the negative x squared plus y squared over 2 dx dy. Now we convert to polar. And this is the integral theta goes from 0 to 2 pi, r goes from 0 to infinity, e to the minus r squared over 2 r dr theta. So you should hopefully remember this from Calc 3. If x and y are in meters, this is meters squared. Meters, unitless. Okay, this is really should be read as dr r d theta, because it's r d theta, that's the length. And now when you do the integration, it's going to become very nice. The theta integral is going to just give you a 2 pi. The 2 actually cancels out nicely over here, and you'll just get a 1 from the r integral, and you get that this equals 2 pi. Therefore, I is plus or minus the square root of 2 pi. Which one is it? Yeah, we're squaring the integral, so when you square things, you can introduce extra roots. Since we're integrating a non-negative function over a positive region, it's not going to be negative. So we will get that it's just square root of 2 pi. And this gives us the normalization factor for the Gaussian. So if we want this to be a probability distribution, we have to divide by square root of 2 pi. Okay. So yes.
Could you maybe go through more steps towards the end of how to complete the integral? Yeah.
Well, this is now a Calc 3 integral.
Right.
So the theta, there's no theta dependence. So the theta integral is just going to give you a 2 pi.
Right. Okay.
And now when you want to integrate the thing, you do a u substitution.
Like u equals r squared over 2, maybe.
Yes.
Okay. So okay. Got it.
And then what's nice is when you take the derivative, the 2's cancel.
Yeah.
And then you'll have a negative sign, so you flip the order, and you'll get an e to the negative u at 0, which is 1, minus an e to the negative infinity, which is 0.
Okay, got
so
it.
This is just Calc 3. Which is, in some sense, my least favorite class to teach because there's too much material for the amount of weeks you have. So the only solution is the solutions are basically to skip material or do the water gun approach. And knowing me, you can probably figure out which approach I choose. Okay, so one of the biggest applications of the technique I'm about to show you is to actually calculate things for probability distributions. I want to use just a little bit more notation. We've already seen some of it with the baseball lecture. So the mean, we'll often write as the expected value of x, or mu of x, if you want to be really specific, is just going to be the integral from minus infinity to infinity of f times the density dx. So this is the average value. The variance, this is going to be the expected value of x minus the mean squared. It's going to basically tell us how spread out something is. And the units we use is, sigma squared. It's going to be the integral from minus infinity to infinity of x minus mu squared f of x dx. And more generally, the kth moment is the expected value of x to the k is the integral from minus infinity to infinity of x to the k fx of x dx. So the hope is that if I give you a nice function, the Taylor series determines the function. If I give you a nice probability distribution, the moments determine the distribution. So hope is the moments determine the distribution. Now, when you take advanced classes with a lot of analytic machinery, you find that there are times when, sadly, the moments do not determine the distribution. And it is possible to have two different probability distributions that have the same sequence of moments. There's a great paper called Can You Hear the Shape of a Drum? And so if you can only hear how the drum vibrates, can you figure out the shape of the drum? And the answer is no. There are drums that are called isospectral. They have the same vibrating frequencies, but they have a different shape. And it turns out that they're, I'll call it isomomental. It's a new word, so don't try to use it in Scrabble. It hasn't been approved yet. There will be isomomental probability distributions that have the same sequence of moments, but are not the same distribution. And they will give different probabilities to different events. Did we look at this function before? G of x equals e to the negative 1 over x squared if x is not 0, 0 if x is... Have we looked at this function? Okay, let's look at this function. Okay? I claim this is one of the 10 best or 10 worst functions in the universe, depending on your point of view. This function is why real analysts have jobs. Okay? What can you tell me about this function?
It's non-negative.
It's non-negative. What happens as x gets very, very large? What does it go to?
Tends to 0.
So as x gets very, very large, it goes to what? It goes to 1.
Oh, yeah, sorry.
Sorry. As x gets closer to 0, what does it go to? Yeah, it goes to 0. It goes to 0 extremely rapidly. Imagine x is 1 over a billion. Then you get e to the negative billion squared. So this function is extremely rapidly converging to 0. So if you were to plot it, if this is 0, it would look something like this. It would look extremely flat. What might you want to calculate for g? G prime. And then after you calculate G prime? G prime. Where's the only place where it's going to be problematic to calculate the derivatives? X equals 0. Any place else, you can just take the standard rules of differentiation. At the origin, this is hard. So we would have to calculate, G prime of 0 is the limit as h goes to 0 of G of 0 plus h minus G of 0 over h. This is the limit as h goes to 0 of e to the negative 1 over h squared over h. How do we calculate that limit? Yes, and this time I'm not going to get upset. This is an okay place to use L'Hopital. It's not circular. You know, last time it was circular. Now, when you want to calculate this, there's several ways you could do it. What I'm going to first do is say that this is the same as the limit as k goes to infinity of e to the negative k squared times k. I'm just letting k be 1 over h. And since this is an e to the negative, I can put that downstairs, and this is just k over e to the k squared. It's the same limit. I'm not doing L'Hopital at infinity rather than L'Hopital at 0. It just looks a little bit nicer and easier for me. And you can now see when I do L'Hopital, I will get that this is the limit as k goes to infinity of 1 over, take the derivative, this will be 2k e to the k squared. The limit is 0. And in fact, the amazing fact is any derivative at the origin is 0. What does it mean if every derivative is 0 at 0?
The Taylor expansion 0.
Yes, the Taylor series expansion is identically 0. So the Taylor series expansion of G at x is the function that's identically 0. Now, let's think a little bit. I know you did Taylor series. Did you guys do much rigorous stuff with Taylor series? So your Taylor series, it's the sum of the nth derivative at 0 over n factorial times x to the n. One of the reasons I want to do this is putting stuff in your refresher bin for Monday's lecture in complex analysis. We're going to need stuff like this. When x equals 0, what's the only term in the Taylor series that matters? The constant term, which you force to be g of 0. So when I tell you the Taylor series agrees with the function at the origin, is this an impressive fact? This is a by definition. By construction, the way the Taylor series is constructed, it must equal the function at 0. I'm not going to say good job, I'm not going to give pats on the back or anything like that. You can't help but agree at the origin. If you agree at one other point, then I'll be impressed. And this is when we start talking about when does the Taylor series converge to the function. The radius of convergence is 0. So if I give you the function x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, what function am I thinking of?
Sine.
I'm sorry?
Sine.
Really? I was thinking of sine of x plus 1701 over 24601 g of x. I like Star Trek, I like Les Miserables. Right? Can you tell the difference between the Taylor series expansion of this and that? No. Because all the Taylor coefficients of this at 0 are 0. Taylor series are not unique. That's a fact you should have hopefully heard when you were looking at Taylor series. But it tells you how dangerous it is and how easy it is to be arguing, oh yeah, this is reasonable. No, we have to spend a lot of time justifying this. So when does the function uniquely specify? What kind of additional conditions do I need? This is one of the reasons why real analysis is so hard. Okay. So now that we've been adequately scared, let's go back to probability. It's not the case that if I know my moments, I know my distribution, but oftentimes it will be. And the moments tell me interesting things about the function I'm studying, about the density. And so the most important one is the mean. You know, whenever you take a class, people always want to know what was the mean, what was the average score in the exam. Then they might ask, what is the standard deviation? When I was a sophomore, I was visiting a friend of mine who was pre-med at Harvard, and she was taking a physics class, and they listed everybody's scores with their ID number so you didn't know who got what. But they gave the mean, the standard deviation, and they actually gave the third and the fourth moments of the distribution, so the grade conscious Harvard students could really compare themselves to their classmates and know just exactly how well they're doing to fourth order. I was really happy I was a yearly at that time. But we'll concentrate for the most part on the first and the second moments. It turns out the variance, you can also write this, it's a nice thing, as the expected value of x squared minus the square of the expected value. And this is just a nice calculation. Just expand this out and you get x squared minus 2x mu plus mu squared. Do the integration and you'll get this. It's a nice exercise to show that this is true. And this in fact shows you how expectation and squaring don't commute. If they commuted, the expected value of x squared would be the same as the square of the expected value. It's not, and that difference is the variance. So the question is, how do we actually calculate stuff like this? How do we actually calculate these integrals? So, differentiating identities, we're finally ready to start doing some examples. So, the first thing is we'll do a discrete application first. We'll start off with an infinite sum. What is the nicest infinite sum you know that has a closed form expression?
1 plus 1/2 plus 1/4.
Good. And in fact, I'm really happy you said it like that with 2. So 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16. That's the one you were thinking of? Okay. And we'll call that S. And in a burst of inspiration, I'll call the next sum T. 1 plus 2 over 2 plus, no, don't do it this way. 0 plus 1/2 plus 2/4 plus 3/8 plus 4/16 plus 5/32. What does that sum equal?
1.
I'm sorry?
Or not 1.
Probably not 1.
That was in the textbook.
Yeah.
You do it, it's 1/2 plus 1/4 plus 1/8 plus 1/2 times that sum plus 1/2 times.
So there is a way to do this by, grouping things and having infinitely many infinite groups, right? So that is a nice way to do it. You can do it as 1/2 plus 1/2. So 1/2 plus 1/4 plus 1/8 plus 1/16, and you can have another one which would be 1/4 plus 1/8 plus 1/16, and then I think 1/8 plus.
Yeah.
So you could do an infinite grouping infinitely many times. There's a better way to do this, and I guess since I'm a professor holding track, I can use the word better. I'm just so trained out by society that I can't say, I have to say all these methods are equally good. There's a cleaner way, a faster way. Now, a lot of it goes back to what we were doing in the previous class. I gave you, I think, you recall, let me see if I can actually recall it. It was equal from 0 to 1 of x to the 5th minus 1 over log of x dx. And I asked you to calculate this. And we found that the best way to calculate this was to replace the 5 with a free parameter t and call this g of t. Or maybe we called it that. And then we found a nice formula for g prime of t. And then we would integrate that and we would get g of t. And then g of t being the integral of g prime of t plus some constant, and we would determine the constant. And so if we're lucky enough to have an explicit closed form expression, we're in business. But the whole idea was to take the problem you're looking at and give yourself a free parameter. So if you want, we can look at a lot of what we're doing as we're trying to incorporate a free parameter. So when I give you 1 plus 1/2 plus 1/4 plus 1/8, if I try to study just that series, I'm in trouble. So I should study something a little bit more general. What do you think I should be studying instead of this series? What should I study instead?
Any geometric series?
Yeah. Yeah. And so, do I want to use X or do I want to use R for my geometric series? Nope, try again. X. So why do I want to use X and not R?
So it's free.
Well, I mean, does it make a difference if I use X or R? No. Could I use the smiley face? Absolutely. My colleagues would laugh at me, but I could use the smiley face as my variable. I want to use letters that remind me of things. I like to use uppercase and lowercase to remind me I have like a derivative, antiderivative pair. When I use the letter X, I'm thinking differentiation. When I'm seeing R, I don't think differentiation as much. So it doesn't really matter. S is going to be the sum of X to the n goes from 0 to infinity, and T is going to be the sum, n goes from 0 to infinity, of n x to the n. Plus 0. And so the question is, how do we get from S to T? And we should, I guess, really give these now functions. So how do we get from S to T? Take the derivative, almost. Yeah, so we're applying the operator x d by dx. So the d by dx lowers the degree of x by 1, and then the x restores that degree. So depending on what you're looking at, a lot of times you use d by dx, sometimes you use x d by dx. It's just which leads to the better. So now we know s of x is the sum, n goes from 0 to infinity, of x to the n, and it's 1 over 1 minus x. So then t of x is x d by dx of s of x. And now I'm assuming I can interchange the sum and the derivative. That can be justified. As long as the absolute value of x is less than 1, I have plenty of convergence. And now I just have to take the derivative of this and multiply by x, and I'll get x over 1 minus x squared. I've done this problem so many times, I just remember the answer. And now all I want to do is I just take the value at a half. And we get 1/2 over 1/2 squared, which is 2. Which, interestingly, happens to also equal s of a half. It's a nice little tweak. If I wanted to change x to be 1/3, not a problem. This is very similar to the generating functions we had with the Fibonacci's, where we could now calculate these weighted sums of the Fibonacci's very easily just by putting in different values because we have an explicit form. All right, so I wanted to put in what s of a half is. So s of a half equals 2. So could these be the probabilities? 1, 1/2, 1/4, 1/8. Could these be the probabilities of a random variable? No, it adds up to 2. So what should I do to make it the probabilities of a random variable? Yeah, divide by 2. So this is going to be a geometric random variable. So the probability that x equals n is going to be 1/2 times 1 over 2 to the n, n greater than or equal to 0. And if I now want to calculate the expected value of x, that's the sum, n goes from 0 to infinity, of n times the probability x equals n. Well, that's just going to be 1/2 the sum, n goes from 0 to infinity, n over 2 to the n. We just calculated that. That equals 2. So we get 1. One of the ways you can look at this, it's sometimes bad to choose 1/2, because with 1/2, you can't tell the difference between getting a head and getting a tail. They're equally probable. If you took p to be 1/3, it would be a little bit better. But what you're really calculating is how many tosses do I need before I finally get a head. So this is the waiting time for the first head. Okay. Now, it's not quite the waiting time for the first head because we are allowing n to be 0. So you would, if you were doing this as a real probability problem, you would not have the sum going from 0 to infinity. You'd have the sum going from 1 to infinity. And then, in fact, then the sum would actually then exactly be 1, and you wouldn't have to put in this factor term. So these are ways to calculate various things. I'm going to do a discrete one again, and then we'll move to some continuous ones. So let's consider the sum, k goes from 0 to n, of k and choose k. We could try to do this directly by expanding out what n choose k is, maybe canceling, maybe pulling out an n, maybe playing some games. But there's a nice way to interpret this. And what we can do is the following. Imagine we flip a coin with probability p of heads and q of tails. Now, if this is a probability, what can you tell me about q?
1 minus p.
1 minus p. So the probability, and say x would be the number of heads in n tosses. What is the probability we observe exactly k heads?
P to the k, q to the n minus k, times n choose k.
Times n choose k. And the convention is just to write the n choose k first. So this is the probability we get exactly k heads. So what must be true about the sum of n choose k, p to the k, q to the n minus k? Do we know what this sum equals? Ooh, I'm on the infinity side.
One.
It's 1. Really, at this point, I want to write it as p plus q to the n by the binomial theorem. And then if q is 1 minus p, it'll just be 1. This is just the binomial theorem. So what this sum is over here is this is essentially calculating the mean when p equals q equals a half. Well, what I can do is I can put in 1/2 to the k, or 1/2 to the n minus k, and then just multiply by 2 to the n over here. And this is now just saying, what's the mean? So the point is, we have this formula here. This sum is equal to p plus q to the n. We can differentiate this. What should we differentiate this with respect to? So if I want to get this sum over here, what should I take the derivative of this with respect to?
Why do we need to derive that?
Well, I want to get k and choose k.
Why can't you just write that as a binomial
And expand out the n choose k? We can't do it as binomial because the binomial theorem is for something of this form. If I have a k here, it's no longer of that form.
Okay.
Right? If I had an n over here, or a 5, if I had something that didn't depend on k, I could use the binomial theorem. And I would just take p equals q equals 1. Or maybe I'm taking them each to be 1/2, and I multiply by 2 to the n. Not a big deal.
Okay.
But what would I want to take the derivative of this with respect to? Now I want to get a k and choose k. Yeah, I could take the derivative with respect to p, and then I'm also going to multiply by p, because that'll keep the power of p to be the k. So I get the sum, k goes from 0 to n, of k, n choose k, p to the k, q to the n minus k, is equal to n, p plus q, and I have an extra p. And this is to the n minus 1. So this is what I get if I take the derivative with respect to p. Now what's interesting is this formula holds for every value of p and q. I don't have to play this game of taking 1/2 and then multiplying by 2 to the n. I could just take p and q to be 1. And so if I take p equals q equals 1, oh, there's my 2 to the n minus 1.
So why is the original sum the mean?
Well, because what I'm calculating here is that if q is 1 minus p, this is the probability I got exactly k heads.
No, but why are you multiplying by 2 to the n?
Oh, because I need this to be, oh, well.
Oh, so you
I
just had a problem.
I originally gave you just the sum of k and choose k, and I'm saying
and then you turned it into a
I can
probability.
turn this into
Okay.
2 to the n times the probability.
Okay, that makes more sense.
Or 2 to the n times an expectation, no longer probability. And now that I have that, I'm just recasting this in terms of something I know. And so if we take p equals, q equals 1/2, we'll get a 2 to the n over here that we pull over. And we get the sum, k goes from 0 to n, of k and choose k is equal to n over 2 times 2 to the n. Because I'm taking p equals q equals 1/2. It's very important when I do the differentiation that I don't take q equals 1 minus p in the beginning, because then I'd have to use the product rule, and it would be a lot more involved. So what I'm doing is I'm keeping p and q both as free parameters. Here's the binomial theorem. And then, once I have the binomial theorem, I apply this method of differentiating identities. That's easy to justify here because it's a finite sum. And so what I can now do is I can get infinitely many more identities from the binomial theorem. I can get a formula for the sum of k squared or k cubed. Lots of things. That's the power of differentiating identities. We now have infinitely many more results from the binomial theorem. And if you think about this, what this is saying is that if you have a fair coin and you toss it n times, I should divide by 2 to the n to make it a probability. How many heads do I expect? N over 2. Expect half the tosses to be heads. It's a reasonable result. Or more generally, if I have probability p of heads, what fraction do I expect? I expect the fraction to be p. Okay, so this is the beginning of differentiating identities. I hope this is showing you how powerful this result is. Right? Let's look at a more interesting one. So let's go back to the Gaussian. So 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared dx. This is the probability density function of a normal with mean mu and variance sigma squared. And we want to calculate things such as, what's the mean, what's the variance. What do you think the mean is of this Gaussian? Mu, right? Based on the fact that I'm writing it as x minus mu, it seems likely that it's mu. And if you think about it, things are symmetric about mu. What do you think the variance is of this? Sigma squared mu. That's probably why I'm writing it like this. You should prove these results. Okay, so I'm going to just concentrate on the case where mu equals 0. So let's say we actually want to calculate the variance. So let's say we want to calculate the integral minus infinity to infinity of x squared e 1 over square root of 2 pi sigma squared e to the negative x squared over 2 sigma squared dx. And instead of calculating x to the 4th squared, we could calculate x to the 4th, x to the 6th, x to the 8th. I'm not really worried about calculating x to an odd power because then the function is odd and it will just be 0. So any thoughts as to how we would do this calculation? There are two good approaches. Any thoughts? One of the two approaches should be obvious based on today's class, right? What's one of the methods? I think it's even still on the board. Differentiate. There must be some identity we can differentiate to calculate this, right? So that's got to be one of the ways. There is another way to do this that you could have done before this class. It's probably our favorite technique to just you can count one. And we all hate partial fractions. It's not a U substitution, it's not a trig substitution.
Just integration by parts.
It's integration by parts. Now if you try to do x squared as u, then du is going to be x, that's great, but oh lord, we would need an antiderivative of e to the negative x squared.
X times.
Yeah, so the trick is you do u equals x, and then dv is e to the negative x squared over 2 sigma squared x dx. And by putting the x over there, now things are fine.
But then, and then you get v.
And then you get, right, and then you'll just get an integral without any x's, and we already know what that is.
Okay.
So it does work out nicely.
Because I've done this before.
Yeah.
And I was like, then we get an e to the negative x squared, and that's really hard.
Right, but we know that now.
Right.
So we're assuming that's known. So let's let the following. The integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2. What does that equal?
A normal distribution of variance 1.
Normal distribution of variance 1. So what would that equal?
1.
Would just equal 1. So if I replace this 2 with the sigma squared, what does it equal now?
It would be a normal distribution of variance sigma squared,
Except I'm not dividing by a 1 over square root of sigma
so it
squared.
should equal sigma.
So it should equal sigma. Now I want to get an x squared. If I take the derivative of this with respect to sigma, what comes down? An x squared. So let's apply d by d sigma. And so we get minus infinity to infinity, 1 over square root of 2 pi. Now we take the derivative of this with respect to sigma. So we'll get a negative x squared over 2. And now we have to take the derivative of sigma to the negative 2. So sigma to the negative 2 will be negative 2 sigma to the negative 3. So the 2 actually cancels. The negative cancels. We have a sigma cubed down here, e to the negative x squared over 2 sigma squared equals 1. I can take 2 of the sigmas and put that inside the square root, because that's what I need for the density. And then the other one I can bring over. And so I can get minus infinity to infinity, 1 over square root x squared, 2 pi sigma squared, e to the negative x squared over 2 sigma squared. I haven't done this wrong.
You're missing the.
Oh, I'm sorry. I bring over 1 sigma.
Yeah.
Because I'm putting inside a square root. So when I bring 1 sigma inside the square root, it becomes a sigma squared. And it gives me a sigma squared, which I can then bring over. So you can actually use this to now very easily calculate the integral of x to the 4th, x to the 6th, x to the 8th, get a really nice formula. And you'll get that the expected value of x to the 2m is 2m minus 1 double factorial sigma to the 2m. So the double factorial means every other. So it's really nice how it works out in this case. So this is the incredible power of differentiating identities. We could do this for other distributions. We can do this for exponential distributions. As long as you have a nice formula that you start with, by applying differentiating identities, you can calculate these means and these variances with great ease. And these are the key objects you need in probability theory. But what I like is it does fit in with what we did on Wednesday. This idea of introducing a free parameter. Even if we only care about the case when sigma equals 1, it's better to have a free parameter. So it's worth pausing for a moment and thinking, why do we want this free parameter? And this comes back to calculus. When you were looking at calculus, you love differentiation. Right? It's one of our most important tools. If your function is defined on a discrete set, you can't do calculus. What's the limit as x approaches y? Well, here's x, and the next closest points are here and here. I can't approach x. I lose all power of gaining results from differentiation. I need to be able to have things vary. I need to be able to take limits. Okay. Any questions about this? We could do weeks of examples of applying differentiating identities to probability. But I just wanted to do enough to just give you a sense. I will end. We've got about 5 minutes left. That should be enough time to do just one other kind of problem. So it's tough for me to read my notes. Integral from 0 to 3, integral from 0 to 2 of 1 over 1 plus m. So like maximum of 3x 2y squared dx dy. All right, so the question is, how would we calculate what this integral equals?
You could split it along the line 3x equals, or you could split it along the line 3x equals 2y.
So the first thing I would do is, before I even split it along the line 3x equals 3y, that'll be our second step. I would first try to make things a little bit more symmetric. So I've got x goes from 0 to 2. I've got y goes from 0 to 3. Let's let u equal 2x. And let's let v equal 3y. And now u is going to go from 0 to 1, and v is going to go from 0 to 1. So whenever I see something like this, my first thought is, can I symmetrize things a little bit so that the roles of the variables are the same? And this would now give me the integral from 0 to 1, integral from 0 to 1, 1 over 1 plus maximum of u, I might as well use u squared v squared du dv.
But u is 2x, and then the problem initially had 3x.
Oh, okay. Okay, so did I just, okay. So x goes from 0 to 2. Do I want maybe u to be 3x? Maybe I want u to be 3x, and now u goes from 0 to 6. And then I want v to be 2y. And then v will go from 0 to 6. Sorry, thank you. And now, as was remarked, this is going to be just twice. And I can divide it along the diagonal. And so in one region, u squared is going to be greater than v squared, and the other one, v squared is going to be greater than u squared. So this will be the region where u squared is greater than or equal to v squared. And so this will be the region where v squared is greater than or equal to u squared. So here, v is going from 0 to 6, and then I will have u go from 0 to v. So I'm going to be integrating like this. And it's going to be 1 over 1 plus v squared du dv. So I'm now just using Calc 3. And I'm just integrating in slices like this. And what's nice is when I do the u integral, I'll get v. And so this is going to be twice the integral. V goes from 0 to 6, v over 1 plus v squared dv. I'm often a little bit excessive, and I write my variables and my integration bounds just so I remember when I have double integrals, which order am I doing things. If I'm doing a double integral, I can't be integrating over v if I've already integrated out v. So if u is a function of v, I've got to do the v integral last and do the u integral first. Well, at this point now, this is not a bad integral. This is a Calc 1 integral. The top is the derivative of the bottom. So this should just be, and in fact, let's bring the 2 inside here, right? Make it really nice. And so you'll get the natural log of 1 plus v squared evaluated at 0 and 6, where the log of 1 is 0, So if I haven't done any mistakes, I think this is like the log of 37. So assuming we haven't made any mistakes, it's just the log of 37. So this is a really nice technique, independent of what we were doing in differentiating identities, but it worked nice for the last few minutes. All right, so we will do complex analysis on Monday.